So let's go ahead and start back up the top for 4. What's 4 squared?
16.
Times 4. Times 4. And then times 4. Good. Any science, computer science people here? Anybody? Computer science people would know this pretty well because it's going to be probably mainly what is all of your size and memory. Usually all comes in pairs or in 4s. All right, what about 5 squared? Well, we're on page 9. Okay, on the notes. Multiply that times 5, you get? Multiply that times 5 and you get? Close. Close. You got 25. Hey, 2 out of 3 is not bad. 2 out of 3. 625. All right, so let's go ahead and look at the bottom row now. 1/8, and we want to rewrite this as an exponential, okay? So, well, do we know what 8 can be rewritten as with exponential? We just did it up in our warm-up. What is it? Do what? Good. 2 cubed, right? So 1 over 2 cubed. Y'all agree with that? Yes. Okay. Now let's see if we can get rid of the 1 over it. Does anybody remember back in Algebra 1 or Algebra 2, talked about inverse functions? What does it mean when it's on the bottom? Very good, Mary. That's right. It means it's negative. So what we can do now is take away the 1 over it. Let's take the fraction away, which we all like that. No more fractions. So what we can do now is we can rewrite it as 2 to the negative 3 power. Good. So take that, guys, and see what you can do with 1 over 25. You'd write down what you did. Right there, please. Thanks. If you take it step by step, like we did in the previous one, 25 can be written as exponential as what? 5 squared. So 1 over 5 squared. And then finally get rid of the fraction. What do you have to do? As Alyssa did here. 1 over 5 squared. Well, I want to get rid of the 1 over, so we go ahead and make it a negative exponent. So it's 5 to the negative 2 power. All right, so let's go and move on to the next one. So with the next one, what did we learn, or what have we talked about, guys, in the past? With powers being raised to a power, what do we do with those two numbers? Say it louder. Exactly, multiply them. So we're going to do exactly that. Is we're going to take this 3 here and multiply it times 2x minus 1. So we rewrite it, guys, like this. Oops. Like that. Well, what do you think we do next? Distribute. Multiply the 3. Exactly. So, distributing that 3. And you end up getting 3 raised to the 6x minus 3. 6x minus 3. Power raised to a power, you do exactly what you guys said, which was multiply. Good. All right? Okay. Not in Algebra 1, but we did talk about this in Algebra 2. So in Algebra 2, you talked about square root, and how can we write that as an exponential function, or as an exponent? So what's square root written as an exponent? Does anybody remember? Do we know the answer to this problem here? What is it? 2, right? 2 raised to what power, guys? 2 raised to what power? 1. The answer is 2 raised to the 1 power, right? That's why we just say 2. We don't say 2 to the first power, correct? Can we rewrite, let's go back to what you just answered earlier. Can I rewrite 4 as maybe as an exponent type of situation? What? 2 squared or 2 to the power of 2, right? Do y'all see that? What do I do with this square? Multiply or divide to get 1. Multiply or divide. You only use multiplication and division. How can we do it? Say that again. Multiply it by 1/2. So the idea now, what do you think square root, what power could I rewrite as square root? 1/2. Yep. So we could do this. Do y'all see that? And using what we just talked about with multiplying the exponents that's raised to a power, what is 2 times 1/2? 1. And that fits exactly what we talked about, right? So let's take that new information. Let's see if we can apply it to what we have here. Let's not do the 125 yet. Let's just focus on the cube root first, okay? So I'm going to write 125. And what do you think it's raised to what power? Say it again. 1/3. Square root, cube root, to the 4th root, 5th root, 6th root, those are all 1/2, 1/3, 1/4, 1/5, right? As you can tell, see, square root was 1/2, cube root was 1/3. Can we rewrite, if you look up at the box you did earlier, is there a 125 that you wrote in the box? 5 to the what? 3rd power? What do we see happens here, guys? They go away, don't they? So what is the 3rd root of 125? 5. I'll let you guys go ahead and rewrite 5 as an exponent, as an exponential function. Square root of 5, how can we rewrite that as an exponential function? Use this maybe to give you a hint for that. Square root of 5 is not 1. Should we write the 2 squared square root? What did we rewrite when you see 2 squared square root? What did we put outside the parentheses? The 1/2. That's exactly right. So what do you think square root of 5 is raised to what power? Close. It is 1 something. Think of the words square. What does square mean? What number is that?
Square?
Square.
Oh, 2.
2. So it's 5 to the what? 1/2. Did you get 5 to the 1/2? Nope.
How'd you get 1/2?
Because square root means what can I multiply times itself? Twice to get 5, right? What's the square root of 4, guys? We did this earlier. How'd you get 2? You found something that multiplied times itself to get 4, right? Multiplied times itself twice. So we don't write it there, but sometimes that's understood too. Square root has an invisible 2 there. Just like what we did over here on the cube root of 125, we put 1/3. With the square root of 5, we're going to put 1/2. It's a fraction. Do you see that? You see it now? Any questions, guys? All right. So if you read on to the box underneath, let me scroll up. States here, just reading through it, a theorem, law of exponents. If S, T, and A and B are real numbers with A greater than 0 and B greater than 0. And this goes back to stuff you guys have already talked about a little bit this morning, which is when you multiply 2 exponential functions, terms, with like bases, what do you do with the exponents? If I multiply 2 exponential terms with like bases, what do I do with the exponents? Add them. That's exactly what's stated here. Do you see that? A to the s power times a to the t power is the same thing as a to the s plus t power. Because we're multiplying, you add the exponents. And this is what we saw earlier. If you raise the power to a power, what are you doing to both of those exponents? You're multiplying them. A to the s raised to the t power ends up being s times t. Now, the next one you got to be careful with, okay? the AB to the S power is equal to A to the S times B to the S. Guys, be very careful here because I see this being done a lot. Is that correct? It's not. Because let me show you an example, guys, and y'all have done this already quite a bit, especially in the last unit. Is x plus 2 squared x squared plus 4? You want to say that. You really do. Because it's easier for the most part. But guys, we know very well if we were to take this and multiply it times itself, what do we do here in order to figure out this product? Multiply what? What's that called, guys? FOIL. If you're taking, and do you know the difference, guys? Can you see the difference between x plus 2 and a times b? Or how about a plus b compared to a times b? What is the difference, guys? Be obvious if you want. There's a plus sign in between them. One has a plus sign in between it. Guys, how many terms are in a plus b? 2 terms. This is called a binomial. Squaring a binomial uses FOIL. How many terms does a times b have? Be careful. It's 1. It's 1 term. Okay? Multiplication does not separate terms, guys. Multiplication just makes it still 1 term. This is called a monomial. 1 term. And when you multiply, raise that to a power, you notice every element of that monomial ends up being raised to that power, right? So be careful. I'm just sending you a big warning advice that I've seen it, that something like this ends up turning like that many, many, many times. Okay? It's always best practice to go ahead and write it twice. Always best practice to do that just because you won't get fooled by the square being there. Okay? Because you can still do the same thing. If I'm looking at, let's look at a monomial real quick off to the side. 3x to the 3rd power. Well, let's just go ahead and expand it. Let's do the long version of this. And now let's look at this. What's 3 times 3 times 3? We're almost there. What's x times x times x? There you go. Okay, do you see the difference between the binomial and the monomial being raised to a power? Good, please recognize that. Okay? All right, so let's move on. 1 raised to any power is going to be 1, which think about it, guys. If I was to expand 1 cubed, what does that expand to? Which ends up being 1 times 1 times 1, which we know anything times 1 is, especially when it's 1 times 1, right? And even more so when it's another 1 involved. But no matter how many 1s you put in there, it's still going to be 1. And then, of course, something we've already talked about, which, guys, this is probably, if you didn't get what we did earlier with the 1 over 8 and the 1 over 25, I want you to star this right here. Because that right there tells you how that works with the negative exponents. If you didn't see that earlier, make sure you star it so you'll see how that kind of works now. And of course, this is always the fun thing and kind of main thing I do in math is I always like to tell my group, hey guys, what's 27 raised to the 0 power? 90% of the people always come back with 0. Oh, it's 0. And they're confident. I feel so bad. But anything raised to a 0 power is always going to be 1. So make sure we know that. Anything raised to a 0 power is 1. Okay? All right. And it goes on to talk about exponential function, the breakdown of it. This will be your initial value. This is how much it's growing. And then this is the rate it's growing at, or how often it's growing, or how fast. It just breaks down exponential function real clearly there, okay? All right, so let's move on to the next page. All right, so now let's talk about solving exponential functions. And the nice thing is, guys, you can solve exponential functions pretty easily as long as they have like bases. If I've got both sides of the equal sign having one term, and that one term on both sides has the same base, then it's simple as dropping the base and writing out the exponents as an equation. So number 1, 7 to the x equals 7 to the x power equals 7 to the 4th power. Well, the 7s are like bases, so they go away, and all you're left with is x equals 4. Which, think about it, guys. How many times do I have to multiply 7 times itself to equal 7 to the 4th power? 4. That should make sense there, right? That equation is set up probably real simple, entry well, to say, hey, how many times do I have to raise 7 to the what power to get 7 to the 4th? That's 4. All right, so let's look at the next one. A little bit trickier on the next one. But you got to remember, guys, the goal is to have like bases. So can I rewrite 8 to match the base of 2 to the x? Yes, okay. What is the base that we need to make it to be? 2. So 2 to the x, let's rewrite 8. So it's 2 raised to what power? 3. And we do exactly what we did on number 1, which is what, guys? Yep, cross out the 2's. I'm going to save this, Parker. So then you have x equals 3 as your answer, right? All right? So make sure you get like bases, and from there it's just a simple drop it, and now you got an equation that you're solving, okay? Next one, a little bit trickier, okay? Ideally, it's one base and match the other. That'd be great. All I have to do is just one number. Can I do something to 16 to make it to the 4th base? What? Right? Is 16 4 squared? Okay. So then we still have to finish off the problem though, right? And that's why that comes in hand. Do you see inside the parentheses what's happened to the 16? The 16's turned to 4 squared. Why did we use 4? Because it's the same base as the left side. You could easily write 16 as 2 to the 4th power, correct? Is that still correct? Is 2 to the 4th 16? Yes, it is. However, it does not match the other base. Now, you can make this harder on yourself, guys, and say, yeah, 4 is 2 squared. So now I have 2 squared and 2 to the 4th power. You could still do that. You're adding a little bit more work, but you can still get away with it. But sometimes if you can just change one side, just do that. And that's what we did here. So what's the rule of thumb if a power is raised to a power, guys? Distribute it. Good. So?
Isn't that 6?
Is it 6?
Minus 6?
Hey guys, keep me in check. I like that. What happens next? There you go. And we're left with? And now we just have a linear function we're solving, right? So 2 moves over. Wow, one step and done. At this point, guys, I highly recommend, especially when getting to exponents, solving equations, because there's a lot of other factors that can mess up. Just real quick, go up to the problem. And let's plug in -6 in for x. So what's 3 times -6? -18. Okay? Let's go over here. What is -6 minus 3? And we realize that 16 can be rewritten as what? 4 squared. What's 2 times -9? Matches. It equals each other, right? You could have plugged that in right there if you wanted to do that instead. You had a choice. All right? On to number 4. How can we rewrite? Well, which side do we need to rewrite, guys? The right side, good. How could we rewrite 1 over 81 with a base of 3? Do what? It's 1 over 3 to the 3, right? Is that right? 9, 27. Nope, it's to the 4th, isn't it? Thanks. However, I don't want 1 over 3 to the 4th. I want 3. There you go, guys. Good. And then you drop the 3's and end up getting an equation and solve from there. Number 5 is not too bad. And the fact that number 5 already has the same bases. Can you see them? What is that base we're looking at? 25. That's nice. 25 is already there for us. So, which side do I need to rewrite? And how do I rewrite 1 over 25 as an exponent? Good. You don't even need to do that. Don't do 5. Just leave it as 25, Adrian. And you could still do 5 squared if you do the other 5 squared. But there's no reason to do that because they already are the same, aren't they? Two would still be fine. Just make sure you do the other side too as well, Adrian. So, power raised to a power. What do we do with that negative 1, guys? Good. So 25, 10 to the x plus 8 power equals 25 raised to the negative 4 plus 2x power. What happens to the 25s? And you're left with another linear function to solve for. Nope. 3 halves. If you divide by 8, you get negative 12 over 8, which reduces to 3 halves. A little bit lengthier on that one. I mean, it was nice the bases were already matching. Yeah, Adrian had a good idea. He said, yeah, we could just go ahead and make this squared, 5 squared, and that 5 squared, and that'd be okay. He's reducing it to the lowest exponent form, and that's fine. I'll let you guys do number 6 and number 7. What's first step on number 6, guys? Good. It's already set up for us. So you cross them out. You end up just solving from there, right? And you get... Aiden, what'd you get? For 6. Correct. What about 7, guys? What do we have to do to 7 in order to make it work? You can reduce it to 2. Is there anything we can reduce it to? Be careful. I jumped in that one too. Because it's 4 times 2 is 8, not 4 squared. Yes. This ends up being 2 squared to the 2x. This ends up being 2 cubed raised to 2x minus 1. So I was gone yesterday. Had to record the lecture on this. And as I'm recording it, I'm like, great. So in the recording, you can hear me sigh real loudly because I was like, it's late. And you also hear my daughter screaming in the background. It's my turn. Sounds great. Really getting a lot done. All right. So let's go ahead and do what we need to do when we raise a power to a power, which is what, guys? That's all right. Distribute. 2 to the 4x. 2 to the 6x minus 3. What happens now? 2's go away. X equals 3 halves power. All right, number 8. Any ideas? Let's work together on this one. Three to the what? 3 to the negative 4 is over here. Good. 3 to the third is over here. I don't know why I wrote a 4. So we're just rewriting numbers. And guys, if you need to, if you don't see that immediately, go to your table that we did on the warm-up. Look for a column that maybe has those two numbers in it. And if you look at the 3's column, you'll notice a 27 and 81. That's going to be your best hint there. So, distribute. So we end up with 3x minus 12 equals negative 4. Being 9. All right, number 10. Number 10, we got to combine two rules together in order to get this. So, with number 10, we see a multiplication on the left side. Yes. Am I mess up?
Yeah, so. Yeah.
Ooh.
3x equals 8.
I was forcing that to work, wasn't I?
Yeah.
So sorry. So ends up being what, 8/3?
Yeah.
Thanks. I'm going to skip the next one because I want to go on to this one. So on the left side, what do you notice? We've got 3 different types of bases. We want them all to be the same. So what base do you think would be the best for all 3 of these? 2. It's hard to do that, to rewrite that as a 4. So let's do 2. So what's 4 rewritten as with a 2 base? 2 what squared? Good. Two, we don't have to do anything. The last one, 16 is what? 2 raised to the... All right. Let's go ahead and remove parentheses here. All right. Following along, guys, so far? So far, so good? Nothing's different. We're just trying to get everything with a like base. We've gotten every number as an exponent. We didn't have to for the middle term because that's already in its lowest form. What do we do now here, guys, on the left side? If you multiply 2 terms together with like bases, what are you doing with the exponents? Good. Adding them together. Right? We're adding them together. So now, since we're multiplying this, did I do 2? Why did I do that? Sorry, guys. I hope you weren't writing exactly what I was writing. It's 2 raised to the x squared power. My bad. 2 raised to the x squared power. So that's why you get that 2 raised to the 2x plus x squared. You have an equation. Both sides have the same base. What do we do with both those bases? Go away. I'm going to move over here. So we dropped the base, and now we're left with what? Right? 2x plus x squared equals 8. We got it to where equal sign has 2's base on both sides, so we just take the exponents and set them equal to each other. How do we solve this? What? Subtract the 8. Because what type of function is this? It is close to that. Quadratic. It is. That's okay. An exponential is present in a quadratic, so you're not completely wrong. That. So what do you do to solve quadratics? Thanks. Yeah, exactly. You guys set it equal to 0 here, and now we factor. Unfortunately, it's a little out of order, isn't it? So let's rearrange it to what we're used to seeing. So what two numbers multiply to get negative 8, but then they subtract to get 2? Bigger number gets the plus sign. Let's finish solving. What's last? And what else? Oops, not 4, but... Negative 4 there. What's there? What makes that equal 0?
2.
What's the degree of a quadratic? What? 2. So how many answers do we have? There you go. Perfect. All right, let's go and finish. Last one. If 5 to the negative x is equal to 3, what does 5 to the 3x equal? Well, to set this up, if 5 to the negative x, let's figure out this equation here. Do we have them as like bases? Yeah. So we can do this, correct? So you stop right here, guys, and you ask one question, that is this. What do I have to do with the left side to make it equal the right side? Y'all follow me? Do we multiply? Oh, I'm sorry. I'll put it up here, guys, so y'all can see what's going on. I asked, what do I have to do with this side to make it match that side? Ali said multiply times negative 3. Remind you guys, we are talking about the exponents here. Do you agree? We are talking about the exponents here, guys. So basically what this means is this. If I raise this to the negative 3, would you agree that I would get that right there? If I was to raise 5 to the negative x, raise to the negative 3 power, what do you do with these two right here, guys? Multiply. So what is negative x times negative 3?
3x.
Positive 3x. So I take this term and I raise it to the negative 3 power. What you do to one side of the equation, you have to do to the other. So with that, what's 3 raised to the negative third? What's 3 raised to the third? 27. Since it's negative, it's what? So the idea is you take what's given to you and set it equal to what you're trying to find out. Set it up side by side and say, what do I need to raise? What power do I need to raise this to get to that? I mean, you could probably go ahead and do away with all this here and just ask that one question. What do I need to do with negative x to get 3x. What do I need to multiply by? Any questions, guys? Good. All right. Unfortunately, since it's been a week since I've seen you guys, we're going to go ahead and dive into transformations. I'll make this as quick and sweet as possible, okay? So looking first off at the graph, you can see here we have an exponential function. And look how the points. I want you to pay attention, guys. Pay attention to the x and y values. The fraction ones I'm going to turn away from because I'm just not really excited about dealing with fractions right now. So I'm going to go ahead and look at maybe the whole ones. What's 2 raised to the 0 power? 1. What's anything raised to a 0 power? 1. So a crucial point, guys, always in an exponential equation, maybe if I used a pen it would work, is 0, 1. Please circle that. A critical point in an exponential function is always going to be 0, 1. Because it doesn't matter what the base is. If it's 10,000 raised to the 0 power, what is the answer to that equation? 1. It will always be 1, no matter what the base is. So what's really unique about exponential functions, guys, what's really unique about exponential functions is this. The base can be anything, okay? When I ask about a parent function of quadratics, does anybody know what the parent function of a quadratic is? X squared. That's it. That's all there is to it. When I ask for a parent function of an exponent, you're going to have to ask me back and go, can you give me the equation that you're talking about? Which means if it was y to the 5x plus 7 power, your parent function would be y to the 5x. If it was y is equal to negative 17 raised to the 2x plus 3 power, your parent function is 17 to the x power. Does that make sense what I'm saying? That base stays the same, and it's only to the x power every time. So it's always different. Parent function for exponents are tricky because that base is always different. It always has to match what problem you're talking about. And that's what's happening here. One more thing that's a crucial point. Raised to the first power. What's 17 raised to the first power, guys? 17. What's 27 raised to the first power? So look at that right there. 1, comma, whatever your base is going to be a critical point as well. Now, it's not as great as 0, 1, because 0, 1 is always going to be 0, 1. However, 1, comma, whatever your base is the other one. All right? And then there's the reverse of it. So there you go. You see that. All right, let's scroll on to the next one.